Hi, my name is Kathleen, and I'm going to be presenting our paper, Fair Together, Mitigating Disparate Exposure in Kemeny Rank Aggregation. I'm going to begin by talking about rank aggregation. Rank aggregation is the problem of taking multiple voter preferences, which are expressed as rankings, and combining them into a single global consensus ranking. As you can see in the image, we have a set of 8 candidates and 3 voters, and each of the 3 voters provides a ranking over all 8 candidates. Then the objective of rank aggregation is to come up with a consensus ranking that represents, in as much as possible, the preferences of all the voters. Rank aggregation is used in several applications across social choice and information retrieval. Specifically, consensus rankings are used to make decisions by committee in hiring, admissions, and award determination settings. For instance, each voter might be a reviewer of candidates who applied for scholarships, and the consensus ranking determines how much money each candidate is awarded. In information retrieval, rank aggregation is used for tasks such as rank fusion and recommendations for multiple users. Both of these combine the results of multiple ranking models. In many of these instances, the order produced by consensus rankings is extremely consequential for the candidates being ranked. Given that rank aggregation is often performed in settings with high societal impact, it's critical to ensure that any discriminatory bias that might be present in voter preferences does not then translate or get aggregated into the consensus ranking itself. Otherwise, critical opportunities or resources might be withheld from marginalized groups of candidates. For instance, in the image we have 2 groups of candidates marked in blue and yellow. As you can see, when the voters produce their rankings, the majority of the yellow candidates are towards the bottom of the rankings. And then when that gets combined into a traditional rank aggregation method, we end up with a consensus ranking that puts the blue group entirely above the yellow group. This is further complicated by the phenomenon known as position bias, which is that when a decision maker looks at a ranking, their attention is concentrated at the top positions of the ranking. So any attempt to mitigate discriminatory bias needs to account for position bias. In other words, fairness interventions must work in the presence of attention decay or drop. For instance, if the consensus ranking orders job applicants, the hiring committee might work down the ranking, filling open positions and stopping once all are filled. The objective of this work is to combine diverse voter preferences into a single fair consensus ranking that satisfies 2 often competing objectives. First, the consensus ranking ensures fairness to ranked candidates in the presence of position bias. And second, it combines all the voter preferences and attempts to represent them in as much as possible. In terms of related consensus ranking approaches, there are many conventional voting rules that do not address candidate fairness in any form. Of the numerous voting rules, Kemeny has received particular attention and popularity due to how it satisfies a number of social choice axioms. The sole objective of methods like Kemeny is to combine all voter preferences into a single consensus ranking. Recently, there have been methods proposed for incorporating candidate fairness into Kemeny rank aggregation. Specifically, pairwise fair Kemeny. Our prior work incorporates pairwise fairness constraints into the Kemeny rank aggregation problem, but this does not address the position bias issue. Additionally, rank aggregation p-fairness is a method which selects a single voter's ranking and re-ranks it to be fair. Its fairness is representation-based and also does not consider all voter preferences since it only selects one voter's ranking. In comparison, in this work, we set out to combine voter preferences to ensure the consensus ranking is fair towards ranked candidates when accounting for position bias. In the paper, we introduced the fair exposure Kemeny rank aggregation problem, whose goal is to find a fair consensus ranking that has a minimum exposure ratio, where exposure ratio is a metric using fairness of exposure that ensures candidate fairness in the presence of position bias. The second component is that the consensus accuracy between the consensus ranking and the voter preferences is maximized. Consensus accuracy is a metric we introduce based on the Kendall-Tau or Kemeny distance. Thus, in the Fair-Exp problem, we constrain fairness while maximizing voter preference representation. Then we introduced two fairness-tunable Fair-Exp methods. Specifically, EPIK, which is exposure parity in Kemeny, is an optimal integer program, which based on the voter preferences and a desired fairness level, finds the fair consensus ranking that has the closest Kemeny distance to the voter preferences. In the paper, we explain how we reformulate listwise fairness of exposure to integrate into the pairwise Kemeny optimization. Next, our second method, EPIRA, exposure parity and rank aggregation, is a near-optimal post-processing heuristic. It first determines a fairness-unaware consensus ranking and then adjusts it to the desired fairness level. In the paper, we formally prove how its properties ensure it minimally lowers the consensus accuracy when adjusting for fairness. Additionally, we experimentally study its performance using 5 different traditional voting rules. Turning to our experiments, we perform a study of our methods compared to alternate approaches mentioned previously. As can be seen in the light blue box, we find first that both EPIK and EPIRA always achieved the desired fairness. And interestingly, we find that methods that are fairness enhanced but with alternate goals can actually introduce unfairness in terms of group exposure in their consensus rankings compared to only the standard Kemeny rule. As you can see here, both pFair-Chem and RAPF have lower and more unfair rankings than the traditional Kemeny consensus. We additionally provide takeaways by conducting a study using the Mallows model. The Mallows model is a dispersion model of voter rankings. So looking at each heat map, we have the reference ranking on the y-axis. So this is the central ranking in the Mallows model. And those range from A to E, and as we increase alphabetically, the central reference ranking becomes more fair. And then the Mallows dispersion parameter phi increases along the x-axis, so we end up with voter rankings that agree more with the central ranking. At a high level, we see with Kemeny, perhaps intuitively, that it only results in fair rankings when the voters are less biased and also have similar preferences, or in other words, they're in agreement and fair, as you can see in the blue box. In comparison, we find that across all agreement and fairness conditions in voter preferences, our methods produce fair consensus rankings. In conclusion, in this work, we introduced the new fair exposure Kemeny rank aggregation problem and 2 fairness-tunable methods for solving it. We also empirically study the performance of our methods and alternate consensus ranking methods on this problem. Both methods provide the best fairness and preference representation performance compared to alternatives adapted to this problem. Lastly, it's worth noting that at their core, candidate fairness and voter preference representation are competing objectives that are specific to each problem instance. In fact, in social choice, the term fairness is used to capture the idea that all voter preferences be comparably represented. We're not able to make statements about the price of candidate fairness compared to voter fairness, since this is ultimately problem-specific. But our methods facilitate weighting candidate fairness against voter fairness and provide alternatives to methods that conventionally always pick the side of voters. Thank you for listening. I'd like to thank my collaborator on this work, Dr. Elke Rundensteiner, and WPI and the NSF. Thank you.